In a previous video we discussed how we can create configuration files for conventional theta to theta diffractometers. But if we take a look at the BGMN documentation, we don't see any configuration options, for example for parallel beam optics, primary beam monochromators or image plate detectors. So does it mean that we can't use datasets of such instruments with Profex? Well, no, we can. But we have to be a little bit creative when we prepare the instrument configuration files. Let's start by taking a close look at the differences of the signal we get from a synchrotron using a 2D image plate detector and compare it to a conventional capillary configuration. On a synchrotron, a narrow polychromatic white beam comes from the storage ring and is shaped by a collimator. It then passes a monochromator and reaches the sample as a thin, parallel and perfectly monochromatic beam, where it illuminates a small section of the sample in the capillary. The secondary beams generate diffraction rings, which are projected on the image plate detector. On the detector plate we get sharp concentric rings, one for each diffraction peak. For clarity, let's just look at a single peak for now. We can convert the 2D image to a 1D diffraction pattern by drawing a line from the center out and plotting the intensity as a function of the angle from the center. The resulting peak has a perfectly symmetric shape. We can draw cross-sections in all other directions as well and sum up the profiles to improve the signal-to-noise ratio. This way we obtain a one-dimensional diffraction pattern with extremely high signal-to-noise ratio. Now let's compare this to a conventional capillary instrument as we can configure it in Profex. The beam coming from the tube's target, which is also called focus in BGMN, is divergent and has a nearly monochromatic characteristic spectrum. If there were no apertures limiting the beam diameter, the primary beam would hit the detector and vastly overpower the diffraction signal. So we limit the footprint using a divergence slit for the equatorial beam height and the beam mask for the axial width. Now we can only see the primary beam as a narrow line on the detector with the shadow of the capillary in the center. The primary beam has the shape of a parallel ribbon and it illuminates the capillary over a length of several millimeters. We get a diffraction signal from the entire illuminated length, which means that the diffraction rings on the detector plate are smeared horizontally. Furthermore, even though the outer shape of the ribbon-like beam is parallel, we can still have divergent rays in the beam due to the finite width of the target. The most extreme divergent rays are shown in red. These non-parallel primary rays further smear the diffraction signal, but we can block them in the primary beam by inserting Solis slits. This cleans up the diffraction signal a bit. We could also narrow the beam by reducing the beam mask, but that would cost a lot of intensity, so it is not ideal. Now when our detector scans from the center out, it will start detecting the off-center curved parts of the diffraction rings before it reaches the centered ring segment. And after reaching the maximum, the intensity falls off sharply. The resulting peak shape is strongly asymmetric. We can reduce the curvature of the diffraction rings reaching the detector by inserting another Solis slit in the secondary beam. This will reduce asymmetry a lot, but there is still some curvature left, and we will not be able to eliminate asymmetry completely at low angles, where the radius of the rings is small and the curvature is strong. But this is a typical configuration we can create in Profex for a capillary setup without a focusing mirror. Now let's try to modify this setup to mimic the diffraction signal we get from the synchrotron image plate as closely as possible. Note that it is irrelevant that the actual configuration has nothing to do with the synchrotron setup. We just want to fake a configuration that generates a similar signal on the detector. To obtain a narrow and parallel primary beam, we first reduce the width of the target, which is also called the focus, to the diameter of the beam. Then we also reduce the height of the divergence slit and the width of the beam mask to the same value. Now we already have a mostly parallel narrow beam profile. We can also strongly reduce the angle of the Solis slits both of them, to block divergent primary rays and curved diffraction ring segments on the detector. Now only a small segment of a centered diffraction ring reaches the detector. We can also insert a pinhole aperture with an opening of the beam diameter very close to the sample to further block divergent and scattered rays. As a last step, we reduce the width of the detector to a very small value to really only measure the center portion of the segment and none of the curvature. As a result, we should obtain an almost perfectly symmetric peak profile. This fake configuration can be used to refine datasets from synchrotron instruments with image plate detectors just fine, as we will see in a minute. There are two more things we need to change, the radiation spectrum and the goniometer radius, but I will show how to do this directly in Profex. This is a scan file of lanthanum hexaboride, LAB6, that was measured on beamline BM16 at the ALBA synchrotron in Spain, and it was kindly provided by a Profex user. And to create the instrument configuration, I will first create a refinement project. So I add the LAB6 phase. And I will just pick any instrument configuration. I will stick with this one. It doesn't matter which one because I will change almost every parameter in this configuration anyway. So I will start with a random instrument configuration. Now I get my control file. And first of all, I want to create a copy of this instrument configuration file with a different name because this is wrong. So I do it manually by going to Locations, Current Project. And this is the instrument control file, the one we want to edit. But I just want to give it a different name, so I create a copy and call it ALBA BM16. And I will use the same name here in the instrument variable. So I save this, and when I go to Instrument, Edit Current Configuration, it will open this file, the SAF file, not the GEQ. This one doesn't exist yet, as long as we haven't calculated the profile. So it will open this file, but it's just a copy of the previous one. So now we edit this configuration. We start with the goniometer, and if we look at the scan file, it was measured from 4 to 17 degrees. So we can create this configuration maybe from 2 to, let's say, 20 degrees. It is not possible to measure much higher with an image plate detector because it's a projection on a flat plane. So 20 degrees should be fine. With the X-ray tube, we specify synchrotron radiation, and the value was provided by the user. This is the wavelength that was used in nanometers. And now we will create a very small target. I don't know the diameter of the beam, but maybe let's assume when it leaves the collimator it's 0.3 millimeters in diameter. So that's just a guess. Let's try that. Then we don't have this slit. The divergence slit we set to fixed. And we position it somewhere in the beam path. The goniometer radius is at the moment is 350 millimeters. So we place it somewhere in between, and we can specify an opening maybe also of 0.3 millimeters. The solar slit we set to a very small value. We don't want to have any divergent rays. So very small opening that only parallel rays can pass. For the beam mask, we place it So the target was at 350 millimeters, this one was at 250, so let's place this at 200 millimeters from the sample, somewhere in between, and also set it to 0.3 millimeters, which is the diameter of our beam. And I also want to place a pinhole aperture with a round hole here, very close to the sample. Let's just place it 1 centimeter in front of the sample with the same opening, 0.3 millimeters. Then the sample is a capillary. I don't know the length, but I know the inner diameter. That was 0.1 millimeters. And the linear absorption coefficient of the material of the sample material, I don't know for this wavelength, but the wavelength is extremely short. It has very little absorption, so I will just leave it at some value. It's probably not relevant for such a short wavelength. It is very relevant for a long wavelength in a capillary setup, so for copper, chromium, cobalt radiation, this is a very important factor, but not for something with wavelength with 0.04 nanometers. We don't have a beam knife, we don't have an anti-scatter slit, but we set the Solar slit in the secondary beam to the same small value as in the primary beam. And for the detector, I want to simulate 1 pixel of the image plate. So I set it to a point detector. Then I don't have to configure anything here, but I have to specify the detector slit. So I want to have a very small opening of the size of 1 pixel. I don't know the pixel size, but typically CCD detectors are in the range of 50 to 100 micrometers. So I will just try with 0.1 millimeter in both directions. So this looks like 1 pixel of a CCD chip. So now I will start the calculation of the profile, and this will take a while to compute. Now we can give it a try and see how good the profile fits, but before we can do that, we need to fix a few things in the control file. There's some parameters that belong to the previous configuration, the one I randomly picked. For example, we don't need this measured background file, so I will just delete it. It's not valid for the synchrotron. Also, we don't want to start at 10 degrees because our measurement starts at 4. We want to use the full range of measured data. So I will comment this line. And one very important thing we have to change in the control file. This dataset was not measured with copper radiation. It was measured with monochromatic synchrotron radiation. So we have to remove this lambda entry and instead enter the keyword synchrotron and enter the value of the wavelength in nanometers. And it was provided by the user who provided the file. And this is the wavelength in nanometers. So instead of using characteristic radiation with the copper spectrum, for example, with the K alpha 1 and K alpha 2 monochromatic emission lines, we are now using perfectly monochromatic radiation by switching from the lambda keyword to the synchrotron keyword and entering one specific value of the monochromatic wavelength. And we also want to change something in the LAB6 structure file. By default, in this specific structure, the lattice parameter A is fixed. This is because it is usually a certified reference material with this A value, but we want to refine it. So I right-click and select Refine Isotropically. And I'm also not interested in intensity matches. I'm only interested in peak shape matches. So I will activate Lebesgue profile fit instead of Rietveld refinement. This is a bit different from Rietveld. It ignores intensities completely and just matches the intensity of the peaks to whatever was measured. And I activate it by typing Lebesgue equals 1. And now it will not try to match intensities, only the peak shape. Now we can run the refinement. So it doesn't get any better than that. It's a really excellent fit. And if we want to keep this instrument configuration, we can copy all these 4 files to our device repository and ideally to our personal repository, because when we upgrade Profex from 4.2.2 to the next version, we might lose any file we copied to this directory if we don't pay attention. This is why we have 2 device directories. This one is in a different location in our personal folder. So I copy it here. And now we have it next time we create a refinement project. But let me explain a few more things. Even though this configuration turned out to be perfect, I want to show a few more things in this file, in this editor here. First of all, if we place a pinhole aperture here, it doesn't really matter what we have before, because it's so close to the sample that we can also skip the mask and the divergence slit. We could deactivate them. We could theoretically also deactivate the solid slit, but I think BGMN will complain and show an error message if there is no solid slit in the primary beam. I'm not quite sure, but we can just leave it in. So we can simplify this configuration a little bit, but I also want to show what happens, what is the influence of the goniometer radius. If I increase this a lot, and synchrotron beamlines can have very long radius, so I can set it to 1 meter, and let's calculate this profile shape. Now we will see the influence of the goniometer radius on the peak shape, but before we start the new refinement, we will remember the chi-square parameter, the value we got with the optimum goniometer radius. It was 0.09. Now let's run it. And the fit is a lot worse. It's 0.9 now. And if we look at the peak shape, we see very wide feet. This is probably air scattering simulated by BGMN when it calculates the peak shape. We have it with all peaks. So if you see this kind of misfit, if the fit looks good at the center and the high parts of the peaks but not at the feet, then it's probably a problem with the goniometer radius. Similarly, when we set it very small and we repeat the calculation, now we see the opposite effect. We see hardly any air scattering, so the peak goes pretty straight down to the background without any recognizable foot. And it's also very wide, so this is a very wrong profile shape. So also the chi-square parameter is much higher. It's now 4.12. And when we optimize this value, we have to do it by trial and error. So we increase or decrease this value and check if the chi-square parameter changes. It's very time consuming because we have to calculate the profile each time. But this is how I ended up finding the optimum at 350 for this configuration, because it just gave me the best fit so verified by just looking at the difference curve and also by monitoring the chi-square parameter. This was an example of how we can fake setups to create configuration files for instruments that differ from the optical configuration supported by BGMN. It is a hybrid approach between the fundamental parameters approach, which describes the instrument geometry to calculate the peak profile, and the traditional approach fitting the generic profile parameters UV and W to a reference dataset. But it can also be used for other instruments, for example lab instruments with parallel beam optics. We just need a good reference dataset to fit the peak profile too. Thanks for watching, and I hope to see you next time. Bye bye.